In this video I will conduct a two-sided test of the dual diode box. And what I mean by that is that the dual diode box will be fully utilized in its intended application, whereby both sides of the box are powered up and receiving the full rated voltage of about 110 to 120 volts. What I have done is connected into 5 kilo ohm load. It's 5 1K resistors in series, and these resistors are connected to the terminal block, and the voltage across the resistors is monitored by this DMM. Power for the LEDs and all of the displays is obtained by an internal power supply that's on the bottom over here, and that internal power supply obtains its power from either incoming power source, either this wire coming into the box or this wire coming into the box. The two DC sources are as follows. The DC source that is controlled by this shut-off box is actually fed directly by real actual solar panels. Currently it is daytime and it is overcast and raining, so the current output capability of the solar panels is not that great, but the voltage is there and it's suitable for our test. The second DC source is comprised of this isolation transformer, which really isn't necessary, but it's in the test setup, and that feeds this auto transformer, whose output I'm able to vary from 0 to 120, and that feeds this shutoff. This is AC coming in. There is a single rectifier, a 6 amp 1000 volt rectifier in this box, and a filter capacitor, a 1500 microfarad 200 volt capacitor with a bleeder resistor, a 300 kilo ohm bleeder resistor, and a switch that disconnects the output. The output of this box is DC, and that feeds the top input of the dual diode box. And again, the 5 kilo ohm load is connected via this plug, and the voltage on the 5 kilo ohm load is monitored here. What I will do now is flip the switch that will apply the solar panel voltage to the 5 kilo ohm load, and at the same time watch the LEDs to indicate presence of power. Okay, so the voltage has gone up to 107 volts. That's the voltage from the solar panels. And one of the LEDs has lit up, indicating presence of power. Notice that none of the bar graphs have illuminated because the 5 kilo ohm load is not consuming enough current. It's consuming less than an amp, therefore since it's 1 bar graph per amp, no bar graphs are turning on. Now I will activate the second DC source. The red light from the isolation transformer is on, so that's live. This is turned down all the way. I will flip the switch. The auto transformer is active. We're still at 108, 107 volts. That's still solar panels. I will apply the output of the auto transformer, the rectified output of the auto transformer, to the dual diode box by flipping this switch. Okay, we still have one LED. And now I will turn up the output of the auto transformer until I exceed the voltage of the output voltage of the solar panels, and that'll indicate to me that the power flow has shifted from the solar panels to the output of the auto transformer. And I'm now cranking up the output of the auto transformer and watching the voltage. I'm going to crank it up until the voltage reaches about 115 volts. Notice the second LED has come on, indicating presence of power. The LED, I expect the LED to come on at about 80 volts. now power is flowing from the auto transformer. It has exceeded the voltage of the solar panels. The voltage from the solar panels is still there. I can take that away at will. And if the voltage from the auto transformer goes away, the solar panels will kick in. And now I will turn down the voltage from the auto transformer. That'll take a little while to die off, and that LED should come off, should turn off. There, the LED has turned off. I will now apply a more substantial load, a 300 watt heater, so I can see the actual transfer of current from solar panels being supplied by solar panels to the auto transformer and back. Okay, I have now taken out the 5 kilo ohm load and replaced it with a 300 watt heater, which is currently off. I've lost the capability to monitor the voltage across the load, but through deductive reasoning we'll be able to tell a lot about what is happening. So I will now, as before, turn on the voltage from the solar panels and apply it to the dual diode box. I should see one LED come on. And we'll wait for the internal power supply to start up. There it goes. I will now switch the heater from off to 300 watts. Okay, even though it should be taking about 3 amps, it's only consuming 1 amp because, like I said, it's cloudy, overcast, raining. The solar panels are not outputting a lot of energy, a lot of current. This is actually good for our case because we can see the transfer of current occur, the transfer of supply of current occur when I turn on the auto transformer. So I will do that now. The auto transformer is turned down. There is power coming out of the isolation transformer. I've flipped the switch on the auto transformer. That is on. I will apply the output of the auto transformer. That is simply engaging the output of the rectifier box. Okay, there might have been some residual voltage on this capacitor. That's why we see the LED come on, even though the auto transformer is turned all the way down. And I will now turn up the output of the auto transformer so that we see the transfer of current occurring. Okay, now the auto transformer's voltage has exceeded the voltage coming out of the solar panels, and it has now usurped the supply of current to the heater. I'll turn it up a little bit more so we get 2 amps. I will not exceed more than 2 amps because the rectifier in this box is rated only for 6, and I don't want to overstress or overheat anything. But when I take away the output of the auto transformer by flipping the switch, the power supply current is now being supplied by solar, and now it's being supplied by the auto transformer. I'll take away the solar, and current is still being supplied by the auto transformer. So the dual diode box functions as expected. It selects from a power source that has greater voltage and indicates presence of power and measures current.